Hello and welcome everyone to another episode of Algorand Developer Office Hours. I'm your host, Ryan Fox, developer advocate here at Algorand, and today I am joined by a couple of my colleagues here at Algorand, Jason Paulos and Russ Fustino. Jason is a software engineer here, and Russ is my colleague on the developer relations team. So welcome to the both of you.
Hey everyone, glad to be back.
You are a maintainer of the PyTeal software, and we thank you for that. And we've got a brand new release that you just pushed out there, so we're going to hear from you in just a little bit. But we are going to start today with Russ, and he's going to be talking to us about Reach, and he's made quite an interesting demonstration dApp, and let's take a look at that.
We're going to talk about Reach here in this segment, and many of you are brand new to Reach, so we'll cover what it is, also why build apps with Reach, and what programming language can I use, and how do I verify smart contracts and audits. These are all questions that typically a developer would have when they're building dApps. And so with Reach, it is a great tool. I can't stress this enough. I'm just floored at how incredible the future looks for this particular product, and I think you'll feel the same way by the end of this presentation for those that are new to Reach. What is it? Basically, it's a programming language that facilitates building dApps, and there's a compiler as well to compile output to any chain with just configuration changes. Mathematically guarantees safety and verification, so we'll cover that as well today. That's a really big plus. And deploying, right? Launches appropriate nodes, runs test simulations. So all these are built right into Reach. So with Reach, you can go ahead and write it once, basically, your dApp, and then deploy it to multiple blockchains, including Algorand, Ethereum, and Complex, and more to come. So I am myself a app developer. I have written iOS, Android, Windows apps. A few of you are online there, Mora, OSU, who've written Swift apps and tutorials for our developer portal. And it came really the analogy between app development and development in Reach, and that's why I've got this cross-platform app development slide up here. Is basically, when I developed apps, I would lean toward products that I would code once and then deploy to iOS and deploy to Android, deploy to Windows. Unity, for example, you can do that, writing it in C# and then deploying it out to all of those platforms, plus a ton more actually with Unity. It's a very, very good product for writing games. I think over 50% of the games in the market are written with that. But nonetheless, Xamarin, React Native, Kotlin, Flow, they all work the same way. It's one common code base and it deploys out to multiple operating systems. With Reach, it's a cross-blockchain deployment and development tool. So it's the same idea. You have one code base, and now you can deploy to, you can deploy to Algorand, or you can deploy to Ethereum. And this is a little bit of an architecture diagram I put together and how it works. Basically, you're going to be thinking in terms of a front end and a back end. The back end is really the Reach code, and it's very JavaScript-like, and that will take care of things like interacting with the smart contracts automatically. So you'll see some interact calls in there, calling out to the methods that are defined in the front end. And then also you have front-end interfaces are defined, as well as the verify and commitment code that you'll see in a minute. On the front end, this can be done in JavaScript, Go, Python. There's actually a remote procedure call support now for that. More languages. I understand C# is just about ready to go too. You have user interface there. This is where you have all the prompts, or web-based UI, or an app-based UI. This is where you can do things like create accounts. You write up the logic, the method logic, and then also blockchain-specific code. So you take both of these, you compile them together, and you're off and running and deploying out to your blockchain of choice. The link at the bottom for the docs.reach.sh, really a good tutorial in there to get started with. So the same code used for deploying to multiple blockchains. And once again, a lot of benefits from doing this. auditing is really huge. If you put your search statements in there, and you put a lot of tests that are things that you're expecting to be true, you can run these and then see if there's any false results coming back on the verification products. Auditors love that, and this is done through the way of mathematical proof, combinations, permutations. Also, there are cryptographic commitment schemes. So if you don't want to publicly display information so that other people can see it at that juncture, perhaps, in your logic flow. Like in our case, we're going to be running a game and we got two people making moves. You kind of want to hide the first person moves until the second one is moved. And then you got, then you can go ahead and show that and participate. Otherwise, the second person would have an unfair advantage. That's kind of the idea there. And then also you got to think about timeouts and non-participation. It's not like going to a website where you just sit there and then you leave and come back a day later, you're still sitting there in the same place. Everything is retained. With blockchain, things are in flux all the time. And if a participant leaves, it could tie up funds that maybe have been dispersed in that contract like halfway through. And now you have a timeout and it's gone, and that money is gone. So these are things that you want to consider when you're building dApps. And then also I got one slide here on platform specific code. What happens if you do want to put something that's specific to Algorand in the code? Well, you can simply do that by checking the standard lib connector and seeing if it's equal to algo or not. And if it is, then you can go ahead and apply the corresponding value in this case to how many rounds I'm going to be looking for. So some things do differ by platform. You do need to have maybe platform specific code. Again, this would be the very minority of the code. It's the same thing, if you're developing apps as well for iOS and Android, with Xamarin, for example, I think 90% of the code is shared and 10% is unique per platform. So I would imagine, you'd have a small percentage there that would be unique just to the platform specific stuff. So I'm going to walk you through an app now. This is an app I wrote called Mora. This is something that we used to play back when I was a kid, even at all of the family picnics and barbecues, and it just seemed like folks would get together behind the barn and play them, or out in the garage and start throwing fingers. You'd have two teams. It goes right down. Each opponent on the team takes a turn against the challenger till the challenger fails, and that goes to the next member. So if your team is the last team standing, you win all the beer, right? And then you get drunk. So no, I didn't say that. There could be alcohol involved in this game. Anyway, so each will guess the total, and this is a little bit of a code. I do want to point you to, when we get to the RPC, we're going to show you first this top one using JavaScript locally and using the standard library as part of that. But you may have a separation of concerns, right, where you've got a front end running somewhere else and you want to talk to the back end. That's where the RPC code comes into play. And you can also do that in JavaScript, but you can see the call here is to the standard library through the RPC call. So it's a remote call. Same kind of call you be doing in Python and Go and into other languages. So very, very flexible in how that works. So let's go ahead and get into the code. And so the very first thing I'm going to do is, when you do your reach init, it's going to generate these two files you see right here. We've got the front end and the back end. And if I just go ahead and run this with the reach run command, you'll see this execute, and then we'll take a look at what's in these two files. This is basically a hello world. It's going to come back and say, okay, hello, Alice and Bob. And so the back end is very, very simple here. You just got two participants that you're going to define this, and you're going to deploy it. Very, very simple. And on the front end, this is where you have things like, you're wiring it to the standard library. This is where the backend is going to be built, right, in that particular index main NGS file in the build folder. And then also you've got the ability to parse currency. Now this will, parse the appropriate currency if you're deploying to Algorand or to Ethereum. And then also you have the ability to create new test accounts with a starting balance in the developer environment, as well as then deploy, right, Alice to the back end, and then Bob's going to attach to it because he's going to be playing it. So this is a simulator. And if you take a look at this build file that got generated, you can go right down here. You can actually see the algo section. So this is all the teal that gets generated for this automatically. And then you also have Ethereum code right down here as well. So you can see all this code just gets generated automatically for you right down there. Okay, the other thing too is when I ran this, you can specify where you want this to run. So for example, there is an environment variable here called reach connector mode, and I'm going to put that in right down here. And so when I run this now, what you'll see are those libraries are actually displaying here when it comes up to run that against Algorand. Okay, so next up, let's go over to something with a little bit of code in it, and this is like kind of the test case. And I basically derived this game from the rock, paper, scissors tutorial that's out on the website. I figured, well, it had the hand part of it where they're doing a hand, which is the number of fingers you throw. And then the only part I really had to add was the number that they're guessing, the prediction of what the total is going to be between the two. All right, so I've got this set up here. I've got, I'm in the Mora one. So let's go just run this. And then we'll take a look at the code that we've got up here. Okay, so now you can see the actual game is being played. So Alice shoots one finger. Bob guesses a total of one, or Alice guesses a total of one. Bob shoots two fingers and he guessed a total of four. So 2 and 1 is equal to 3. So the result of this is a draw, right? Nobody wins. Nobody guessed the amount, and it only went through one time. And this is where you start defining the logic to the game. And here is, my logic that says, okay, if both of them are equal, both guesses are equal, then it's a draw. Otherwise, if you add them together, then, guess A wins it, and so forth. If it's B, then B would win, and everything else is a draw. So that's what I came up with in terms of my logic. This is what, again, we're looking at the backend file right here. So I've got a player defined where each player is going to be able to call, get the number of fingers and get a guess, then also see the winning and see the outcome, which you would see down below right there. And then we got the use of interact. So here we're going to interact with the front end, right, to get fingers. And if I go to the front end, this is where you would see these methods starting out. So this is just a random function that we're calling here to get the number of fingers. And then we're displaying information here in the console that you see down below. Get guess takes a argument. So this would be passing in the fingers that you guess, because if you yourself threw out two fingers, you don't want to be guessing 0 or 1 because you've already thrown 2. So it's got to be, it's got to be greater than 2. So it's going to take an educated guess. Okay, I'm going to take the number of fingers you had plus another random number for the number of fingers left. Now, I'm just keeping this small in this example. I'm only allowing him to throw 2 fingers. So the total max would be 4, just so we can see the results come out quicker and just get the test logic down. So in this one, basically, if I did do that reach connector mode, let's take a look at this. We're going to do this again. We're going to run this with reach. You can see up above that it actually was invoking the Ethereum modules, and now this time it's invoking the Algorand libraries. All right, so that part's all set. Now let's get into a little bit more depth with our example. So what about a while loop, right? And what about things like validations and assertions? We talked about all this, right? So if we take a look at this, what you want to do is start out with the logic that's in, make sure we got the right ones we're looking at. Let's close everything up here, bring up more 2. And now you can see I've got some asserts. Now what the asserts does is basically this first one, for example, This is a real world, play. So if Alice throws a 0 and Bob throws a 2 right down here, right? And then Alice guesses 0 and Bob guesses 2, then Bob wins the total, right? Is thrown is 2, right? So then Bob wins, and a few other scenarios. And then you start getting into these for all combinations. And when I go to run this, you'll see that these are all mathematically checked. And this is the kind of logic you need to put in the back end when you are developing a dApp with reach. So here you see you got the for all for all the fingers in A, all the fingers in B, and then you can go ahead and guesses for all the guesses for A and all the guesses for B. So there is the outcome. You have to have a win or a draw, right, is going to come back. Same thing here. I'm passing in the 2 parameters where both guesses are the same. And in that case, it's always going to be a draw no matter really what the other ones are. Now I've got a couple of other functions. I got a timeout function as well that I've added here. And also I've got a logger I've introduced on the back end to log information out should you need to do that with debugging. And also what you see here is the main flow, all right, for both A and B. So this is both of our participants, Bob and Alice. We're going to say, okay, we're going to check this timeout logic that we got on the front end. And then also we are going to then publish this wage. And when we do that, then we're going to take this, and then Bob's going to make his move. And then you can see we've got the interact log. So that was what we had above. This has logger function right down below. So you can print things out in the back end that are happening. So that helps you when you're debugging. Here we've got a deadline to publish in for our commits and our timeouts. And then also we've got the unknowable, which is pretty important. So in this case, Bob does not know the values of Alice, but Alice does know the values. So this is what I was talking about, where if Alice goes ahead and publishes her number of fingers that she has at this point right here, and then does a commit, publish these to the blockchain, then Bob would have an unfair advantage because he would know that. Instead, what we're doing is we're going to make a commitment by using a salt value and this, and then we're going to go ahead and then do a make commitment call, and then that is going to be the thing that we're going to publish. So it's not known and it's encrypted there. Then finally, Bob makes his call and then interacts, and then we go ahead and publish all the information out for both. And then we go ahead and see, you can see it right there. So we're going to declassify that secret information that we had up above. And now we can play the game and compare these two with to see what the winning number is right there. And that's what gets published. The other thing I wanted to point to is the fact that we have, if I go and do a reach debug, there is another variable for debugging that you can use. So I'm going to get in the right directory here. And let's do this. And if I do reach run now, you'll actually see debugging information that gets displayed down below too. And then you'll see that all displayed right here. So you can see all the detail calls coming out, as well as some of the other calls, right? So this will go ahead and run. Sometimes this goes for a little bit because I am using all 5 fingers in this particular version. And there it is. And Bob and Alice complete the game, and Alice wins that one. So to turn off the bugger, just set it back to nothing. And let me just do this again. We'll go ahead and reach run this without the debugger content. And then you'll see the actual game unfold with all that. So this is the line that just printed off on the back end with that interact method. And let's show you the front end now right here. So these 2 folks are still playing. You got Alice shoots 3 fingers, guesses 7. He's got 5. So again, they keep shooting until there's a winner. So we actually facilitate that through a while loop that we have that goes through until that there is a winner. So you can see that in our method there. Now, if we come back over to the back end, excuse me, the front end. So now you can see I've flushed out, I put a little bit of a delay in to cause some timeouts to test that accordingly. And then we also have the random function here where we're going to do that again for both players. We've added the timeout logic, right? Observe the timeout, that gets kicked in. And then also we've got, the balance afterwards using the get balance method call on each one of those. So that's where you see everything displayed down below. Okay. So there's one thing I really want to point out that's very, very big here. Now, if I go down to the transfer logic, this is going to, both of them are betting, right? So we added wagering to this example too now. And so each one, donates, 5 algos to the pool. And so now there should be 2 wagers in there. And so now if I change this, say to 1, and I go to run this again, now you're going to start getting the value of all those asserts that we had placed in the logic here. And you're going to see that this is actually going to fail. And it says right there, verification failed. Balance 0 at application exit is not happening, right? So there's still funds in there. So we created an account that was created from scratch. We added funds to it. If we were to publish this and have that information correct and have it not be checked, there would be algos that would be locked up on this particular contract that you're never able to get at. And this is a very serious thing, and you want to really write responsible code. And what's the equivalent? Well, you can hire an auditor to do this. And a lot of smart contracts, that's been the approach to date. The auditor, though, now would just have to really focus on your assert statements and making sure that all of the combinations and permutations are tested for in the assert statements that you have. And then if you do a new feature, then you just do additional asserts for the new feature that you might have. So this really makes the whole world of testing and participation and deployment safe by doing this. And this is a feature you can't undermine and purpose it, because it's very valuable. So that's it. So now if I go change that back to 2, it's going to work. If I use 3, same thing. It's going to say, no, you got too much going on here, and it's going to complain about that as well. Okay, so that's that part of it. Lastly, let's take a look at the RPC. So if I go to the Go section now, the nice thing about this is this backend file that we created. This is exactly the same backend file that I just used when it was using the local JavaScript libraries, right? So that doesn't change whatsoever. What changes, this is a Go example written in Go, is that I could go ahead now and execute this. Now there's a command to go ahead and install the RPC client. Then after you run that, then you simply run the app. So let's get over to that directory and go ahead and paste this in. So now we're going to do a reach run, and now you can see the verb change from just reach run to reach RPC run, and then we're going to specify which file that we're going to use. And so now what you can see here is this is actually executing in Go. You can see it checked all those theorems up on top. And then it accepts the wager 5. You got Alice fingers being guessed, and this will keep going until there's a winner. So if you take a look at this client-side code, how is it different? Well, like I alluded to in the PowerPoint, now you have all of these RPC calls to get to parse the currency to create the new test account. And it's going to be using the standard lib still, but it's going to be done remotely. So very, very great interface, provides a lot more functionality because you're, doing this in the language of choice. I can also show you one here I got for JavaScript, just to show you the difference between what we have been looking at so far and the RPC version. And then let's go ahead and hit the reach run here. Or excuse me, I got a new command for this. JavaScript. Those that are trying this at home, I did have to set one environment variable up. This node TLS rejected for testing purposes. So if you get an error running this again, that's the trick there. And then finally, let's just go ahead and there's an npm install, which puts there's a node module directory. You can see right here that generates. So, and now let's just go ahead and run this. Now this one here, I set up debugging on. So you should actually see the RPC calls. I think if it's debugging equals 0, I think you get the RPC calls. 1, you get RPC plus everything you saw the last time, which is every little item. But now every RPC call you can see being listed here, and then you can see the game being played out as well, and you can see exactly what's happening when and where. So that's about it for my session. I'm going to wrap up with a quick summary slide here and see if we got any questions. Again, you want to sign up for that developer newsletter if you haven't done that already. And then also we've got a lot of Gitcoin bounties and grants up at the Algorand Foundation has been running. And so if you go out to Gitcoin and click on Algorand Foundation, who's the company that's responsible token economics, that would be a good thing to do. Take a look at all we got out there. Lots of great ambassadors. I know plenty are on the call here today. If you want to become one, contact Stephen at Algorand Foundation. And then our dev portal, you want to go ahead and get at. And we got the link to this deck as well. Ryan, can you post that in the chat window, this PowerPoint bit.ly? Yep. And then here's the code that I just show you. It's up on Algorand DevRel Reach Morra Game.
That was outstanding. Good stuff, Russ. Thanks so much.
Cool. You're welcome.
Well, welcome up to the stage now, Jason Paulos. Again, he is my colleague here at Algorand on the engineering team, and he's going to talk to us a little bit about the latest release of PyTeal. So that's release 0.8.0, but importantly, it brings in the features of Teal version 4. And I think we get to see some looping, some subroutines. Anything else you got up your sleeve today, Jason?
Those are the two big ones, yeah. I will show you a little bit about what the new features are and jump into some live coding and show you how you can use these for yourself in PyTeal.
All right, let's do it. Thank you.
Great. Okay, yeah. So PyTeal is a Python library that Algorand has created in order to make creating smart contracts in Teal easier to do. And you can do that from inside of Python. And so here is the Python project page that you can read more and download it from. And importantly, as Ryan mentioned, we just released 0.8.0 about a week ago. And this update, this long-awaited update, adds support for some really exciting new features from Teal 4 that were released in AVM 0.9 a few months ago, I think. And the two biggest ones that I'm going to highlight today are the ability to loop in Teal and to have subroutines, which are both highly requested features, and we're really excited to actually enable these use cases, and I will show you that pretty soon. But first, I just wanted to point out, this is the PyTeal documentation site. We've got some great information here, including if you go to the control flow page over here, we've got in-depth explanations for some of the new features. So we have in-depth explanations for while loops and for loops, as well as exiting loops and how subroutines work and how you can use them in interesting ways. So this is a great resource to check out. You can get there from our main page by just hitting this docs button. And I encourage everyone to explore this if you're interested in PyTeal. Great. So without further ado, we can jump into the demo portion that I wanted to show everyone. And basically what I have here in front of me is the beginning of a PyTeal program. It's pretty much a basic skeleton right now. I've got my approval program as a function here, and I also have a clear state program that just approves everything. And then down here, I have some code to compile each of these programs, my approval program, my clear state program, and then just write those to a file so I can actually deploy that, that teal file that it creates. And importantly, since I'm using the latest version, I can specify teal 4 as my version here, and that will let the compiler give me full access to these new features, which you'll need to do if you want to use loops and subroutines in your teal programs. Great. And so I've fleshed out the approval program a little bit. This is a pretty simple thing in terms of PyTeal so far. Basically, the path that we care about is if on completion is no op, and then I'm going to jump to this on call expression that I defined here. And then in all the other cases, I'm going to reject if it's an opt-in. And I'm only going to approve the dangerous actions, update and delete, if the creator of the app is doing that. And so that's just some basic safety measures for this demo. And I really want to focus what happens on a normal application call. And so for this example, we're going to be implementing factorials in 2 different ways in PyTeal. And so I have a global state operation up here that's just going to put factorial of 6 as the key, and the value will be, hopefully after we implement one of the functions above, our program will actually compute the factorial of 6, put that into local state, or sorry, into global state, and then we can expect and inspect that and make sure that it's the right thing. Okay, so let's start with this first function, factorial iterative. And what we want to do is compute the factorial of our argument n using loops, and then return that. So that will get called here. But the first thing we want to do actually is tell PyTeal that this is meant to be a subroutine. And subroutines in PyTeal are essentially like functions. They're going to be bodies of code that you can define once and then call multiple times from your program. And those multiple subroutine calls will use the same code in order to create the result that you're computing. So prior to that, you could do things like this where you break up your PyTeal program into multiple functions. However, every time you invoked a function, it would copy the entire code inline into the place you invoked it. So it wasn't very efficient because you have essentially a bunch of code duplication inside your program. So in order to declare that this is a subroutine, we just need to add the subroutine decorator, which is new, and the newest version of PyTeal. And we need to tell it what type that it returns. So in this case, we're going to return a uint64 from our subroutine. And I will add this to the recursive version as well. And that is all we have to do to let PyTeal know, hey, this is a subroutine. I'm going to be calling this from my program. And instead of actually copying and pasting the entire implementation, PyTeal, the compiler, will compile this separately and then add it into your program at the appropriate place. Great. So let's actually implement this. So the first thing that we're going to do is we're going to want to loop from 1 through n and multiply each of those values and add them to a temporary value that will then return at the end. And so the way I'm going to use this, the way I'm going to do this is by using scratch variables. And so these are PyTeal objects that represent a slot in scratch space, which is a teal concept of temporary space that you can use and put variables when your program executes. So we're going to make a uint64 scratch variable for my iterating variable, and I'm also going to create something called product, which will store the product of my different factorial components, and I'll return that at the very end. All right, and then I'm going to create and return a sequence which will contain all of the PyTeal operations for the subroutine. And so the first thing I'm going to do is I'm going to store 1 in the product variable, just because this is what I'm going to need to start out. Oops. And the next thing I'm going to do is actually start my loop. So I'm going to use a for loop for this example. And we're going to store integer 1 in my loop variable I. My condition is going to be I.load is less than n, since that's, or I guess less than or equal to n, since that's the argument that I'm going to compute the factorial of. And then I'm going to, in my step, add 1 to I and store that into I again. Okay, and then I can add finally the do portion of this for loop. And this is going to contain the loop body that gets executed every time that this loop runs. And so what we want to do here is we want to store a new value in my product variable. And that value should be the product of what is currently in the product variable and I, since that's the value that I'm looping towards. So I will do product.store, product.load times I.load. And what will happen there is first it'll do, 1 times 1 and then 1 times 2 and so on, and compute the actual factorial product of all of those. And then at the very end, I can just return product.load, and this should compute the factorial and actually return it for use in my program. So why don't we make sure that this compiles and then try to run it on the chain on testnet, and hopefully we can inspect the result and it should be right. So the factorial of 6 should be, I believe, let's see, 720. So that's the value that we're going to be looking for on the chain. So I just compiled it here. I've got another tab open with Sandbox running on testnet. And so let's see. I'm just going to copy in the TEAL program. I guess we can inspect this really quickly just to show you what's going on here. So we've got some normal kind of PyTeal generated code. And then I will show you, let's see, right here, there's something called call sub, which is the TEAL opcode to actually invoke a subroutine. And so we go to sub 0. This is the implementation of factorial iterative. And then here's the actual body, including the loop that actually computes the factorial and returns it with red sub right there. And so if I were to call this function multiple times, let's see, where'd it go? That would simply just be adding multiple versions of call sub into my program. So it would add barely any space at all and reuse the implementation for this subroutine right there. Great. All right, so I copy that in. And let's actually create an app using my approval program. And hopefully that should compute the factorial and save it to the chain. So let's do that. Oops, didn't mean to do that. OK, so it created an app with this index in that round. So I will just copy that. I'll go to Algo Explorer. I'm going to drop this app ID in there. And we can see this is the approval program that I was just showing you. And we have application global state. And yep, the key is factorial of 6, and it's pretty small, but hopefully you can see that the value is 720. So this did work, which is great to see. And all right, so we've got factorial iterative down, and it's working great, at least for that one, that one input of 6. But I'm sure it generalizes to others as well. And now I want to show you how to do this using recursion in subroutines as an alternative. And so obviously in prior versions of PyTeal, since we didn't have subroutines, it was impossible to do recursion on that since you only have the main program and you can't re-enter the main program. But now with subroutines, you can do recursion in pretty complex ways in order to create a program. So I'm going to be implementing the same thing, factorial, but using recursion this time instead. So let's see, we're going to return a sequence. And in that sequence, I'm going to add a base case for my recursion. And that base case will be if my input n is less than or equal to the integer 1. So this will be either if it's 1 or 0, since all integers are unsigned. Then I'm going to return 1 for my factorial, since 0 factorial equals 1 factorial, which is equal to 1. That's my base case. And then my recursive case is going to be, if the base case wasn't hit, then I'm going to return n times factorial recursive of n minus 1. And so this is just the basic factorial definition. We're returning the current argument n times the factorial of n minus 1. And that should be all that's required in order to implement this recursively. So I will just copy and paste this. So let's change this print message a little bit. So we're going to call this iterative factorial of 6 and recursive factorial of 6. And let's change this factorial recursive. And so I'm going to, let's see, go back to my other terminal, run Python again to compile this. And I will show you demo approval.teal. And now I've got call sub 0 and sub 1. And so sub 0, let's see, where is sub 0 going to be? It's up here. It's still factorial recursive or iterative, the same as before, but now we have sub 1, which is factorial recursive that implements this using recursion. And so let's create a new app and submit it to the chain. And hopefully we should see 2 values in the global state, and they should both have a value of 720. So let's do that again. Fingers crossed. All right, we're pending and created a new app with that ID. So let's head back to Algo Explorer, paste in that ID for testnet, and then we can inspect the global state. And yep, iterative factorial 720, recursive factorial also 720. And so these two things are going to compute the same value of the same factorial, but using just different implementations, which is a really cool feature of PyTeal 4, that you can actually do complex recursion in iteration like this. And I hope this enables a lot of fun use cases going forward for all the PyTeal developers out there.
Outstanding, Jason. Well, thank you very much for whipping us through that. Very insightful, showing us the latest release of PyTeal, recursion, and also subroutines. Very important. It really helps make the code more efficient. You can do a lot more. So we got to see a couple of different languages and compilers that are all compiling down to Teal here today. They're similar, but they're different. Maybe either one of you want to kind of talk us through what are the differences between PyTeal and the Reachlang?
Yeah, basically with Reach, you're generating dApps. With PyTeal, you're generating Teal. And so Teal is part of it, right? That's a smart contract part of it for sure. And the Teal that gets generated can be used with the SDKs and so forth to build solutions with. And the flip side is with Reach, you basically have code that's on the back end that looks and feels like JavaScript. And then the front end could be done in any language. And I think when it comes to things like verification, correct me wrong if I'm wrong, Jason, but I don't think PyTeal would have that kind of facility where it can go through and make sure that this contract is emptying everything out, because there might be other pieces to it that make the whole thing come together. Is that safe to say?
Correct, yeah. That's just a verification is outside the scope of what PyTeal is doing. Its main goal is you can write a program in Python and I'll compile it to Teal for you. And so a lot of things that Reach does address are outside of the scope for PyTeal.
Got it. Well, good. We've got a question here that has to do more with the protocol layer here, but this has to do with infinite loops. You know, kind of what are the dangers now that we have this ability to do recursion? How is Algorand protecting against somebody locking up the chain by putting in this infinite loop?
Yeah, that's a great question. So even though we have added these two pretty powerful features, recursion and looping, your app still has a maximum budget of like 700 compute units. And basically iteration and looping, or iteration and recursion doesn't change that. So you could write an infinite loop, but after you reach your budget of 700, the chain stops executing your code and ends that transaction and fails it, which is the safe thing to do. And in the case of recursion, the same thing applies, but it's actually, we do a really cool thing where we don't actually limit the recursion depth at all. But because, due to the 700 compute units, that's kind of a limit on the depth being 700, at least because it takes some compute units to call a subroutine and return from it. There's like an implicit limit there, but we don't have a maximum recursion depth of 50 or 100 per se. It's all about how much resources are you using, and as soon as you exceed that, we stop executing the code and fail that transaction.
Wonderful. That's good. Well, we won't lock up the blockchain due to this enhancement for certain. Do you have any experience? Have you run it through its paces? Do you know kind of what does that 700 plus compute units equate to? Like what can you do, and when have you run out?
Right. You can do a pretty large amount of basic operations, since in Teal, most operations that are basic cost 1 compute unit. So you have up to 700 to play with there in an individual app call. It does get a little harder if you want to do cryptographic operations like compute hashes, verify signatures, things like that, since those have a much larger cost, since they're significantly more complicated. And I will say, coming down the pipe, we do have plans to kind of not specifically increase the number of compute units across the board, but rather pool the compute cost in a transaction group. And so what I mean by that is you may have an atomic transaction group with 4 application calls, and maybe the first one only uses 100 units. Then the others can use the remaining 600 units from that first app call, as long as on average the whole group uses less than 700 per app call. And so we think that flexibility is going to enable you to have maybe a more advanced, a longer app call as one of your group, but a bunch of simpler app calls in the remainder of the group.
Very good. And then on the Reach front, I know that the Reach compiler and the checking that it's doing when it's doing its compilation is giving you a warning. If it computes that a particular branch of execution would go over those compute units, it'll give you a warning and say that we'll need to simplify this program in order to make it actually execute on the blockchain. So Reach will tell you ahead of time.